Hello everyone, I'm Jasper. Here I'll walk you through how to create a latent terrain from scratch. So make sure to have the unknown terrain external installed correctly, and as always, we'll be using the Rave model from Exit AirCam. We'll be using the one called Percussion, so if you have been following along the tutorial series, you should have that model already, but if you don't, just make sure to have it downloaded from this link. We'll be following the instruction on the building terrain from scratch page. So we'll go back to Max and we'll be using a two-dimensional control space as an example. So we'll create an unknown terrain GUI object, graphic user interface, and this will be our X and Y pad, which is a two-dimensional X and Y coordinate system as the basis of our terrain. So now let's create an unknown tilde object with the percussion model and use the decoder only. And as you can see that it gives us 4 latent dimensions, so we know that our terrain model will need to produce a 4-channel latent signal as well. So in our unknown terrain object, the first 2 arguments will specify the number of dimension in the control space, in this case is 2, and the number of latent dimension, which is 4. So now we have a terrain with 2 inlets. We'll connect them to our X and Y pad. And for the outlet, the first 4 of them will be the latent signal, so we'll connect them to our decoder. And as usual, we'll use a multi-slider to visualize our latent vectors. So now we have a basic setup, but at the moment our terrain won't produce anything that makes sense because it's currently empty. So if you plot them, it won't have any terrain at the moment. So we'll need to train it with latent trajectories and spatial trajectories. So we'll create a subpatch called dataset, and we'll start from the latent trajectory. So the easiest way to do this is to use a polybuffer object to manage a list of buffer. You can also use a single buffer object if you just have one buffer to load, but I'll use a polybuffer here and I'll name it all buffers. So I'm going to add some jump loops in my polybuffer. So the behavior of a polybuffer is that if it gets a dump message, and it will output all of its buffers, and it will contain a list of information about each buffer. So here, the first item is an index, and then the name, the file path, and the length in millisecond, and so on. And here we're mostly interested in the name of the buffer and the length of it, because the length of the buffer will also affect the length of latent trajectories. So in order to get these 2 pieces of information, we'll need to use a zl.ins object, and that will get the item at the index 2 and index 4. This is a 1-based indexed system. And then we'll prepend a append keyword at the beginning. So now if I have 2 message boxes, and it will add the buffer name and the length to them. And next we'll convert all of this buffer into latent trajectories. So there are multiple ways of doing that, but we'll be using the unknown terrain encode object. And make sure to load the Rave percussion model here. And we'll connect the list of buffer name to it. So you'll see that it has 3 outlets, and the first one will give us a dictionary to tell the current list of buffer that is being encoded. So we can use a dictionary.view to display it. And the second outlet will tell us how many latent vectors can be produced by these buffers. And the third outlet will be a dictionary of all of the latent vector encoded from the buffer. That is the thing we need. So we'll use a dictionary object to capture that. And now I'll click on the list of buffer name, and you can see that it already calculated how many latent vectors we'll get from each buffer. And now we'll use a encode message, and this will basically do a forward pass of the encoder, and we'll get the latent vectors in this dictionary. This is basically a JSON dictionary, and we have two other buffers, so that has given us two latent trajectories, and each of that will have 4 dimensions. And now we'll do the spatial trajectories. So we'll use the unentering GUI object again, and make sure to set the behavior to dataset, and make sure to set the value boundary to what you need. I'll just stick to the default. So the first thing we'll need to do is to make sure that the length of our latent trajectories and the spatial trajectory match, because we don't want either of them to be longer or shorter than the other. We can do that simply by passing the length of our other buffers to our GUI, and this should be numbers in milliseconds. You can also manually set the latent length attribute here to specify how many latent vector do you have, but here we'll just pass in the length in millisecond. You can see that as I click on the message, the latent lengths are automatically calculated, and this matches the set of numbers we got from the encoder object. So now we can start to plot our trajectories in our GUI. And this is to say that I would like the first audio buffer to be plotted along this line. And since we have defined the length of our trajectories, so if it gets too long, you see it won't get any longer because we have run out of latent vectors beyond this point. And you can see that if it turns blue, that means we have used all of our latent vectors. And if it's gray, that means we haven't plotted all of them. And it's okay if you have some of them left out, and they just won't be used during training. And we'll plot the second trajectory as well. And if you press the Command key or the Shift key while clicking on this point, it will add one of these anchors, so we can create some irregular shapes, and that might, make our terrain more interesting. So once this is done, we can create another dictionary object, and we'll call this one coordinates. So the last outlet of the GUI will produce a dictionary of coordinates along these two lines. So if you're using the latest version of the unentering package, every time you change something, it will automatically update this dictionary. So if that's not the case, I would strongly recommend to grab the latest version of the package, or you can use the get content message to get this dictionary updated. Alright, so now we have these two dictionaries as our dataset. So we can copy them and go back to our main patch and paste them here. So we can send a ban message to get them into the terrain object. We should be able to see that in the console, you see 2 spatial and 2 latent trajectories are loaded. So now we can start to do the training. We'll use a train message for this, and every time it sees a train message, it will start to build the terrain for a few epochs. So now if I plot it, you can see that it started to take shape. And we're just going to use a metro to keep this going, and we can plot the terrain after each train message. So if you're familiar with deep learning, you know that we can monitor the loss, which means the amount of error during training. So in the last outlet of NN terrain, it provides some logging information. We can route that to loss, and in that way we see that our model is having some progress. So after a while, I'm just going to pause the training and make sure to set our terrain to enable and set the NN tilde to enable as well. And now if I move my mouse on this X and Y pad, it's going to do the latent spacewalk inside the terrain. Alright, so if you would like to save the model, we can use the checkpoint message, and that will save the terrain under the name we have put here in the saving name attribute, and also in the folder you've put here as well. So that was how to build a terrain from scratch. It was quite a basic setup, so I do encourage you to go into the help files. There you can find some more in-depth explanations of the parameters and the interfaces, and as well as some of the demo applications which will be uploaded to the online documentation page soon. So thanks for watching, and I'll see you next time.